Now, in this lecture, we find out the radius of a circle using two different methods. In the drawing, we have triangle ABC that blocks the circle, or the circle is inscribed by triangle ABC. In addition, we know that this angle ABC equals to 60 degrees in its side, and this is angle ACB that is equals to 75 degrees, and side BC of triangle ABC equals to 2 units in its length. Again, our mission is to find out the radius R of this triangle ABC. So we start with the first method, and we'll do a construction, that is to say from point C, we'll draw perpendicular on side AB. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB as D. By doing this construction, we created the right triangle DBC. So I copied the right triangle DBC in a new page and we will analyze it. So actually, this is triangle DBC that I copied from the original drawing. Angle DBC equals to 60 degrees, and side BC equals to 2 units, according to what is given us the question. This right triangle DBC, cosine 60 degrees equals to DB over BC. So I write it down. So cosine 60 degrees equals to dB over BC, and BC is 2, so it is, we substitute BC by 2, and we get that cosine 60 degrees equals to dB over 2. Cosine 60 degrees is 1/2. So 1/2 equals to dB over 2. We multiply this equation by 2 and we get that dB equals to 1 unit in its length. So this line segment dB equals to 1 unit. We'll continue to focus on the right triangle DBC. On the right triangle DBC, sinus 60 degrees equals to DC over BC. Sinus 60 degrees is square root of 3 over 2 and it equals to DC over BC, and BC is 2. So in conclusion, we found out that square root of 3 over 2 equals to DC over 2. We will multiply this equation by 2 and we get finally that DC equals to the square root of 3 units in its length. So here, this line segment DC equals to the square root of 3 units in its length. We continue to focus on the right triangle DBC. On the right triangle DBC, the sum of the angles must be equal to 180 degrees. So which angles we have inside the right triangle DBC? We have this angle that is equal to 90 degrees plus this angle that is equal to 60 degrees. 90 degrees plus 60 degrees, it is 150 degrees. So the missing angle here must be equal to 30 degrees in its size in order to complete the sum of the angles in this triangle DBC to 180 degrees. The missing angle here must be equal to 30 degrees. So it is given as the question that the big angle ACB equals to 75 degrees in its size. This is the big angle ACB. So the big angle ACB minus the small angle DCB will be equal to the missing angle ACB. Repeat again. The big angle ACB minus the small angle DCB will be equal to the missing angle ACB. So the big angle is equal to 75 degrees minus the small angle that is 30 degrees is equals to the missing angle ACB. So 75 degrees minus 30 degrees, it is 45 degrees. So the missing angle here, ACB, equals to 45 degrees in its size. So I'll write it down. The missing angle ACB equals to 45 degrees in its size. In the next step, I will copy the right triangle ACD in a new page and we'll analyze this right triangle ACD. So actually this is the right triangle ACD that I copied from the original drawing. We just right now found out that angle ACD is the missing angle that equals to 45 degrees in its size, and we have already found out that side DC of this triangle ADC equals to square root of 3 units in its length. The sum of the angles in this triangle ACD must be equal to 180 degrees. So which angles we have in this triangle ACD? We have this angle that is equal to 90 degrees plus this angle that is equal to 45 degrees. So 90 degrees plus 45 degrees is equal to 135 degrees. Therefore, the missing angle here must be equal to 45 degrees in its size. In order to complete the sum of the angles in this right triangle ADC to 180 degrees, the missing angle here must be equal to 45 degrees in its size. Those two angles are both equal to 45 degrees, therefore they are equal to each other, and we have the rule that in front of equal angles in the triangle there are equal sides. Those two equal angles are located in front of those two sides, so those two sides must be also equal to each other. So side AC, and again those two equal angles are located in front of those two equal sides, so those two equal sides must be also equal to each other. That is to say, side AD must be equal to side DC. AD equals to DC. But we have already found out that DC equals to the square root of 4 units, so I can write here that DC equals to the square root of 4 units. And from this equation, AD equals to DC equals to the square root of 4 units. We will get that AD is also equals to the square root of 4 units in its length. So AD equals to the square root of 4 units in its length. You can write down in the original drawing that I segment AD equals to the square root of 4 units in its length. We will continue to focus on the right triangle ADC, and we will implement the Pythagoras theorem on this right triangle ADC. Here by PT is a version for Pythagoras theorem. According to the Pythagoras theorem, the right triangle ADC, AC squared, that is the square of the hypotenuse, equals to AD squared plus DC squared. So AC squared equals to AD squared. AD is equal to 3, therefore AD squared is equal to 3 squared, that is 3, plus DC squared. DC is equal to 3, therefore DC squared is equal to 3 squared, that is 3. So in total, AC squared equals to 3 plus 3, that is 6. AC squared equals to 6. We take a root of this equation, and finally we get that AC equals to the square root of 6 units in its length. AC equals to the square root of 6 units in its length. Here, side AC of triangle ABC equals to the square root of 6 units in its length. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is described by triangle ABC, that could be any triangle, the radius R equals to the area of triangle ABC that blocks the circle over S, that is the semi-perimeter of the same triangle, triangle ABC. And the semi-perimeter of any triangle is the perimeter over 2. The drawing of this rule number 15 is this. So in the drawing we have a circle with radius R that is inscribed by triangle ABC. And according to this rule number 15, the radius R of this circle that is inscribed by triangle ABC will be equal to the area of triangle ABC that blocks the circle over the same perimeter of the same triangle, triangle ABC. So we can actually implement rule number 15 in our drawing. Why? Because whenever we have a circle that is inscribed by a triangle, we can implement rule number 15. So, according to rule number 15, the radius R of this circle that is inscribed by triangle ABC will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. Repeat again. The radius R of this circle that is inscribed by triangle ABC is equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. The area of any triangle is the base of the triangle times the height to the base over 2. And you have to divide it by S, that is the semi-perimeter of the same triangle, triangle ABC. So we'll take the base of this triangle, triangle ABC as AB. AB is the base according to our choice. And the height must create 90 degrees with the base AB. Here, line 7 CD creates 90 degrees with the base, therefore CD is the height to the base. So the height is CD divided by 2 and all divided by S, that is the semi-perimeter of triangle ABC. So here AB is square root of 3 plus 1. Times CD. CD is equals to the square root of 3 in its length. All divided by 2, and we have to divide it by S. So actually, this expression is the area of triangle ABC, and we have to divide it by S, that is the semi-perimeter of the same triangle, triangle ABC. The semi-perimeter S is equals to the perimeter over 2. So the semi-perimeter S is the perimeter, and the perimeter is AB plus BC plus AC. And if we divide the perimeter by 2, we get the semi-perimeter S. So found out that this expression is the area of triangle ABC over the semi-perimeter. The semi-perimeter is AB plus BC plus AC over 2. So AB equals to the square root of 3 plus 1 plus BC equals to 2 units in itself according to what is given as the question, plus AC. AC equals to the square root of 6 units all divided by 2. So the value of this expression is the area of triangle ABC, and the area of triangle ABC is the value of this expression that is actually equals to 2.366 square units. That is the area of triangle ABC, and the same perimeter is of triangle ABC equals to the value of this expression in the denominator, and the value of this expression is equals to 3.591 units, and 2.366 over 3.591 is equals to 0.6589. In conclusion, found out that the radius R of the circle is equals to 0.6589 units. Repeat again. The radius R of this circle is equals to 0.6589 units. In the next step, I will present to you how to find out the radius R of this circle according to the second method. In the second method, we define the center of this circle as O. We define the point of tendency of tangent AC with this circle as F. We define the point of tendency of tangent AB with this circle as E. And finally, we define the point of tendency of tangent BC with this circle as D. Point O is the radius. Point O is the center of the circle. Point D is the point of the circle itself. Therefore, OD is the radius of the circle that we defined as R. And here we have rule number 1 that we can implement on our drawing. According to rule number 1, a tangent a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So we have here tangent AB, that is tangent to this circle at point M. Point M is the point of tendency. And we have the radius OM that is drawn to point M. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to this rule number 1. We can actually implement rule number 1 in our drawing. Why? Because in our drawing we have the radius OD that is drawn to point D, that is the point of tendency of tangent BC with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. Likewise, we join points O and D together by a straight line. OE is the radius of this circle that is equal to R according to our definition. And we have the radius OE that is drawn to point E. Therefore, according to rule number 1, this angle equals to 90 degrees and this angle equals to 90 degrees. Likewise, we join points O and F together by a straight line. OF is the radius of this circle that is equal to R. Again, the radius of it is drawn to point F. Therefore, according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. We can implement here also rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have a circle in the drawing, and the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA equals to PB. We can actually implement rule number 2 in our drawing. Why? Because in our drawing, if we focus on the common external point, point C, from the common external point, point C, we have two tangents to this circle, tangent CD and tangent CF. And according to rule number 2, they are equal to each other. That is to say, CD equals to CF. According to rule number 2, CD equals to CF. Likewise, if we focus on the common external point, point B, from the common external point, point B, we have two tangents to this circle, tangent BD and tangent BE. And according to rule number 2, they are equal to each other. That is to say, BD equals to BE. BD equals to BE according to the same rule, rule number 2. In the next step, we join points O and C together by a straight line. And we join points O and B together by a straight line. we will prove that those two right triangles can go into each other. That is to say, we'll prove that the right great triangle, triangle BEO, is congruent to the yellow right triangle, triangle ODB. So I write it down. We'll prove that the green right triangle BEO is congruent to the yellow right triangle OBD. So why the green triangle is congruent to the yellow triangle? First of all, OE equals to OD. They are both the area of the circle, therefore they are equal to each other. OE equals to OD. So side OE of the green triangle equals to side OD of the yellow triangle. They are both the radii of the circle, therefore they are equal to each other. Repeat again. OE equals to OD, they are both the radii of the circle, therefore they are equal to each other. In addition, BE equals to BD according to rule number 2. Again, BE equals to BD according to rule number 2. Side BE of the green triangle equals to side BD of the yellow triangle according to rule number 2. Repeat again. BE equals to BD according to rule number 2. And finally, we have the common side, side OB. OB is a common side that belongs to both triangles, so we can write down that OB equals to itself. Repeat again. OB equals to itself as a common side that belongs to both triangles. So, we actually proved that all the three sides of the green triangle OBE are correspondingly equal to all the three sides of the yellow triangle BOD. Therefore, we actually proved that those two right triangles can go into each other according to side rule. So the green triangle BOE is congruent. This is the sign of congruent to the yellow triangle, triangle OBD. According to side rule. And from the fact that the green triangles can go to the yellow triangle, we will derive that those two angles must be also equal to each other. Again, we derive that those two angles must be also equal to each other. So this is angle EBO in the green triangle, and it is equal to this angle OBD in the yellow triangle. Repeat again, angle EBO equals to angle OBD. So if we define one of those two angles as theta, then the other angle must be also equal to theta because they are equal to each other. Okay. So this is angle theta plus the other angle that is also theta. In total, they must be equal to 60 degrees. Theta plus theta, that is 2 theta, equals to 60 degrees. So here we divide this equation by 2 and finally get that angle theta equals to 60 degrees over 2 is 30 degrees. So actually, this is angle theta that is equal to 30 degrees in its size. In the next step, I will copy the right triangle OBD, the right yellow triangle OBD in a new page, and we will analyze this right yellow triangle OBD. So actually, this is the right yellow triangle OBD that I got it from the original drawing. Side OD is actually the radius of the circle that is equal to R, and this is angle theta that is equal to 30 degrees in its size. So in this triangle OBD, tangents 30 degrees equals to OD, this point B, OD over BD. OD is R, so it is R over BD. So tangents 30 degrees equals to R over BD. Here we will multiply this equation by BD, and we'll get that BD times tangents 30 degrees equals to R. Here we'll divide this equation by tangents 30 degrees, and finally we'll get that BD equals to R over tangents 30 degrees. So this My segment BD equals to R over triangle 30 degrees in its length, so I write it down here. Side BD equals to R over triangle 30 degrees. Likewise, we repeat on the same process on those two right angles. That is to say, we will prove that the right orange triangle, triangle ODC, is congruent to the right pink triangle, triangle OFC. We'll do it quickly because it is exactly the same process as we did on those two right triangles. So we prove that the right pink triangle, triangle ODC, is congruent to the right pink triangle, triangle OFC. Again, the right orange triangle, triangle ODC is congruent to the right pink triangle, triangle OFC. So, write those two right triangles congruent to each other. First of all, OF equals to OD, they are both the radii of the circle, therefore they are equal to each other. OF equals to OD. In addition, CF equals to CD according to rule number 2. Again, CF equals to CD according to rule number 2. Here, CF equals to CD according to rule number 2. And finally, OC is the common side that belongs to both triangles, so OC equals to itself. It's the common side that belongs to both triangles. So we actually prove that all the three sides of the pink triangle OFC are correspondingly equal to the three sides of the orange triangle, triangle ODC. Therefore, those two right triangles can go into each other according to side rule. So I write it down. The pink triangle, triangle OFC is congruent to the orange triangle, triangle ODC. According to side rule. And for the fact that the pink triangle is congruent to the orange triangle, we derive that those two angles must be also equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. So this is angle FCO in the pink triangle. And it is equal to this angle that is actually angle OCD in the orange triangle. And again, angle FCO equals to angle OCD. So if we define this angle as alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha, that is 2 alpha, equals to 75 degrees in its side. I write it down, 2 alpha equals to 75 degrees. We divide this equation by 2, and finally we get that alpha equals to 75 degrees over 2, it is 37.5 degrees. So actually, this is angle alpha, that is equals to 37.5 degrees in its size. In the next step, I'll copy the orange right triangle ODC in a new page and we will analyze it. So this is the right orange triangle, triangle ODC that I copied from the original drawing. Side OD is the radius of the circle that is equal to R, and this is angle alpha. Angle OCD is angle alpha that is equal to 37.5 degrees. So in this right triangle, triangle ODC, tangents 37.5 degrees equals to OD over DC. So I write it down. Tangents 37.5 degrees equals to OD over DC. OD is R, so it is R over DC. So we actually found out that tangents 37.5 degrees is equals to R over DC. Here we'll multiply this equation by DC and we'll get that DC times tangents 37.5 degrees equals to R. Here we will divide this equation by tangents 37.5 degrees. And we get that DC equals to R over tangents 37.5 degrees. So I actually found out that DC equals to R over tangents 37.5 degrees. This line segment DC is equals to R over tangents 37.5 degrees in its length. So I write it down here that DC equals to R over tangents 37.5 degrees. From the drawing, it is very easy to see that BC equals to BD plus DC. So I write it down. BC equals to BD plus DC. Repeat again. BC equals to BD plus DC. BC equals to 2, according to what is given as the question. And it is equals to BD. BD equals to R over tangens 30 degrees. Plus DC. DC equals to R over tangens 37.5 degrees. So actually, in conclusion, we found out that 2 equals to R over tangens 30 degrees plus R over tangens 37.5 degrees. We take out R as a second factor from those two expressions, and we get that 2 equals to R. So R was taken out as a second factor from those two expressions. So inside the brackets we have what is left from this expression of 32.48 R as a second factor. What is left is actually 1 over tangens 30 degrees. Plus 1 over tangens 37.5 degrees. So what is left from R over tangens 37.5 degrees after we took from it R as a second factor? What is left is that it is actually 1 over tangens 37.5 degrees. So in conclusion, we found out that 2 equals to R times 1 over tangens 30 degrees plus 1 over tangens 37.5 degrees. So 2 equals to R, and inside the brackets we have 1 over tangens 30 degrees is equals to 1.732 plus 1 over tangens 37.5 degrees. 1 over tangens 37.5 degrees equals to 1.3032. So in conclusion, we found out that two equals to R. Inside the brackets we have 1.732 plus 1.3032. So 2 equals to R, and 1.732 plus 1.3032 equals to 3.0352. In conclusion, we found out that 2 equals to R times 3.0352. We divide this equation by 3.0352 and finally we get that R, the radius that we are looking for, equals to 2 over 3.0352. This actually equals to 0.6589 units. In conclusion, we found out that the radius R of the circle equals to 0.6589 units. That's actually the same result as we found in the first method. Repeat again. In both methods, we found out that the radius R of the circle equals to 0.6589 units. Okay. In the next step, I will summarize the lecture. We'll start In the first method, of course, in this lecture we found out the radius r of this circle. In the drawing we have triangle ABC that blocks this circle, or the circle is inscribed by triangle ABC. In addition, we know that angle ABC equals to 60 degrees, angle ACB equals to 75 degrees, and side BC equals to 2 units. Again, our mission is to find out the radius r of this circle. So in the first method, we did the construction, that is to say from point C, we draw perpendicular on side AB. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular for point C on AB as D. By doing this construction, we created the right triangle DBC. So I copied the right triangle DBC in the new page, and we analyze this right triangle, triangle DBC. This is the right triangle DBC that I copied from the original drawing. In this right triangle DBC, cosine 60 degrees equals to dB over BC. Cosine 60 degrees equals to dB over BC. So it is dB over BC, and BC is 2. So it is dB over 2. So cosine 60 degrees equals to dB over 2. Cosine 60 degrees is 1/2. So 1/2 equals to dB over 2. Here we multiply this equation by 2, and finally found out that dB equals to 1 unit in its length. This line segment dB equals to 1 unit in its length. We continue to focus on the right triangle, triangle DBC. On the right triangle DBC, sinus 60 degrees equals to DC over BC. Sinus 60 degrees is square root of 3 over 2, that is equal to DC over BC, and BC is 2. So in conclusion, we found out that square root of 3 over 2 equals to DC over 2. We multiply this equation by 2, and finally found out that DC equals to the square root of units in its length. Here, this line segment DC equals to the square root of units in its length. So, we continue to focus on the right triangle DBC. On the right triangle, triangle DBC, the sum of the angles must be equal to 180 degrees. So which angles we have in the right triangle, inside right triangle DBC? We have this angle that is equal to 90 degrees, plus this angle that is equal to 60 degrees. 90 degrees plus 60 degrees equals to 150 degrees. So the missing angle must be equal to 30 degrees in its size in order to complete the sum of the angles in this triangle, triangle DBC to 180 degrees. So it is given us the question that the big angle ACB in the right column, this is the big angle ACB that equals to 75 degrees. The small angle DCB equals to 30 degrees. So the big angle minus the small angle must be equal to the missing angle, ACD. Therefore, the missing angle equals to 75 degrees minus 30 degrees, that is 45 degrees. Angle ACD equals to 45 degrees in its size. Then I copied the right triangle, triangle ADC in the new page, and we analyze this right triangle, triangle ACD. This is the right triangle, triangle ACD. That I copied from the original drawing. the sum of the angles in this right triangle, triangle ADC, must be equal to 180 degrees. So which angles we have inside the right triangle ADC? We have this angle is equal to 45 degrees, plus this is a right angle. So 90 degrees plus 45 degrees, it is 135 degrees. So the missing angle must be equal to 45 degrees in order to complete the sum of the angles in this right triangle ADC. So 180 degrees, the missing angle must be also equal to 45 degrees in its size. So we have those two angles, they are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, they are equal sides. So those two sides that are located in front of those two equal angles must be also equal to each other. That is to say, side AD must be equal to side DC. But we have already found out that DC equals to the square root of 3 units. So we can write here that DC equals to the square root of 3 units, and from this equation AD equals to DC equals to the square root of 3 units, we derive that AD also equals to the square root of 3 units in its length. Here, this side AD equals to the square root of 3 units in its length. We can write here that AD equals to the square root of 3 units in its length. Continue to focus on the right triangle, triangle ADC. On the right triangle ADC, according to the Pythagoras theorem, AC square equals to AD square plus DC square. So AC square, that is the square of the hypotenuse, equals to AD square. AD is square root of 3, therefore AD square is square root of 3 square, that is 3, plus DC square. DC is square root of 3, therefore DC square is square root of 3 square, that is 3. So in total, AC square equals to 3 plus 3, that is 6. AC square equals to 6. We took out of this equation, and finally found out that AC equals to the square root of 6 units in its length. Here, side AC of triangle ABC equals to the square root of 6 units in its length. In the next step, I presented to you a new rule and implemented the new rule in our drawing. The new rule is rule number 15. According to the new rule, the radius of a circle that is described by triangle ABC, so the radius R equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. The semi-perimeter of any triangle equals to the perimeter over 2. So the drawing of rule number 15 is here. So we have this circle with radius R that is described by triangle ABC. So the radius R of this circle, according to this rule, rule number 15, will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. We can implement rule number 15 in our drawing. Why? Because in our drawing we have a circle that is described by a triangle. Whenever you have a circle that is described by a triangle, you can implement rule number 15. So the radius R of this circle will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. I repeat again, according to rule number 15, the radius R of our circle that is described by triangle ABC equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. The area of any triangle is the base of the triangle times the height over 2. So, all divided by S, that is the semi-perimeter of the same triangle, triangle ABC. We choose the base of this triangle, triangle ABC as AB, and therefore the height is CD. Why? Because CD creates 90 degrees with the base AB. Repeat again. The base is AB and the height is CD divided by 2, or divided by S, that is the semi-perimeter of triangle ABC. AB equals to the square root of 1, to the square root of 3 plus 1. AB equals to the square root of 3 plus 1 times CD. CD equals to the square root of 3 units, all divided by 2. So in total, the area of triangle ABC equals to AB to the square root of 3 plus 1 times the height that is square root of 3 divided by 2. All divided by S, that is the semi-perimeter of the same triangle, triangle ABC. And the semi-perimeter of triangle ABC is the perimeter, that is AB plus BC plus AC over 2. AB is square root of 3 plus 1, BC is square root BC is 2, according to what is given as the equation, and AC is square root of 6, all divided by 2. So this expression is the triangle ABC, and the value of this expression is 2.366, and this expression is actually the semi-perimeter of triangle ABC, and the value of this expression is 3.591. So 2.366 over 3.591 equals to 0.6589. So the radius R of this circle equals to 0.6589 units. Then the next step I actually presented to you how to find out the radius R of this circle according to the second method. In the second method, we define the center of this circle as O. We define the point of tendency of tangent AB with this circle as E. We define the point of tendency of tangent AC with this circle as F. And we define the point of tendency of tangent BC with this circle as D. We join points O and D together by a straight line. Point O is the center of the circle, point E is the point on the circle itself, therefore OD is the radius of this circle is equal to R, according to our definition. And we have the radius OD that is drawn to point D, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule number 1. Likewise, we join points C and D together by a straight line. EO is the radius of this circle that is equal to R, and we have the radius OE that is drawn to point E, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and F together by a straight line. OF is the radius of this circle that is equal to R. The radius OF is drawn to point F, that is, and therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Then, we implemented rule number 2 in our drawing. From the common standpoint, point C, we have two tangents to this circle, tangent CF and tangent CD. And according to rule number 2, they are equal to each other. That is to say, CD equals to CF. CD equals to CF according to rule number 2. Likewise, we focus on the common external point B. From the common external point B, we have two tangents to this circle, tangent BD and tangent BE. And according to rule number 2, they are equal to each other. That is to say, BD equals to BE. Again, BD equals to BE according to rule number 2. Then we join points O and C together by a straight line, and we join points O and B together by a straight line. In the next step, we proved that the green triangle, the green right triangles can go to the yellow right triangles according to side rule. I'll repeat again on the proof quickly. EO equals to OD, they are there on the circle, therefore they are equal to each other. In addition, BE equals to BD according to rule number 2, again BE equals to BD according to rule number 2, and finally, side OB is a common side that belongs to both triangles, so we can write down that OB equals to itself is a common side that belongs to both triangles. We actually proved that all the three sides of the right triangle OBE are correspondingly equal to all the three sides of the right yellow triangle, triangle OBD. Therefore, those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if one of those two angles is theta, then the other angle must be also equal to theta because they are equal to each other. So theta plus theta equals to 60 degrees. Theta plus theta is 2 theta, that is equal to 60 degrees. 2 theta equals to 60 degrees. We divided this equation by 2 and finally found out that angle theta equals to 60 degrees over 2, that is 30 degrees. So actually, this is angle theta that is equal to 30 degrees in its size. Then I copied the right yellow triangle OBD in a new page and we analyze this right yellow triangle OBD. This is the right yellow triangle OBD that I copied from the original drawing. In this right triangle OBD, triangle is 30 degrees, equals to OD over BD. OD is R, so it is R over BD. Times 30 degrees equals to R over BD. Here we multiply this equation by BD and found out that BD times times 30 degrees equals to R. Here we divided this equation by times 30 degrees and finally found out that BD equals to R over times 30 degrees. So here this line segment BD equals to R over times 30 degrees. We repeated on the same process on those two right triangles. We prove that those two right triangles can go into each other according to side rule. Repeat quickly on the proof. OF equals to OD, they are both the radii of the circle, therefore they are equal to each other. CF equals to CD according to rule number 2. Here CF equals to CD according to rule number 2. And finally, CO is a common side that belongs to both triangles, so CO equals to itself is a common side that belongs to both triangles. So I actually prove that all the three sides of the pink right triangle OFC are corresponding equal to all the three sides of the right orange triangle ODC. Therefore, those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we will derive that those triangles must be also equal to each other. So if one of those triangles is alpha, then the other again must be also equal to alpha because they are equal to each other. So alpha plus alpha equals to 75 degrees. Here, 2 alpha equals to 75 degrees. We divided this equation by 2 and finally found out that angle alpha equals to 37.5 degrees. This is angle alpha that is equal to 37.5 degrees. In the next step, I copied the right orange triangle ODC in a new page and we analyze this right orange triangle ODC. This is the right orange triangle ODC that I copied from the original domain. This right triangle ODC times 37.5 degrees equals to OD over DC. Again, times 37.5 degrees equals to OD over DC. OD is R, so it is R over DC. Times 37.5 degrees equals to R over DC. Here we multiply this equation by DC and finally found out that DC times 37.5 degrees equals to 1. Then we divided this equation by times 37.5 degrees and finally found out that DC equals to R over times 37.5 degrees. Here this line segment DC equals to R over times 37.5 degrees. From the domain, it is very easy to see that BC equals to BD plus DC. Again, BC equals to BD plus DC. BC equals to BD plus DC. BC is 2, BD is R over times 30 degrees, and DC is R over times 37.5 degrees. So we found out that 2 equals to R over times 30 degrees plus R over times 37.5 degrees. So 2 equals to, we took out R as a common factor from those two expressions. So inside the brackets we left only with 1 over times 30 degrees plus 1 over times 37.5 degrees. So if we found out that 2 equals to R times 1 over times 30 degrees plus 1 over times 37.5 degrees. That is to say 2 equals to R and 1 over times 30 degrees equals to 1.732 plus 1 over times 35 plus R over times 37.5 degrees, this is actually 1.3032. So we found out that 2 equals to R times 1.732 plus 1.3032. So 2 equals to R and 1.732 plus 1.3032 equals to 3.0352. We divided this equation by 3.0352 and finally found out that R, the radius of the circle that we are looking for, equals to 2 over 3.0352. That is actually 0.6589. So we found out that the radius of the circle equals to 0.6589 units. So in both methods we found out that the radius R of the circle equals to 0.6589 units. Okay, thank you very much.